Hi everyone. So in this video we are going to start studying about combinational circuit. So very interesting chapter and very important chapter as well. And before studying this chapter, I highly recommend to revise the previous notes. You need to revise the logic gates, K-maps and Boolean algebra, all those topics and number system. Then only you should come to combinational circuits. So here we will be using everything that we have previously studied. So what is a combinational circuit? So in the first chapter I told you we will make an IC. And how we will make an IC? By interconnecting the logic gates. So in combinational circuit, this is what we do. We do the interconnection of logic gates. So this would be our IC. And what this interconnection why we are doing this? So that in this particular IC, if we give some particular input, it can produce some particular output. So there will be m bit input and it can give us n bit output. Now m and n can take any value. 2 bit input, 1 bit output, 2 bit input, 3 bit output, 4 bit input, 7 bit output, 4 bit input, 1 bit output. So some particular input will be there and some particular output we will get. And these output will depend on the present condition of the input. Let's just say initially my input condition is 1, 0, 0, 1. So these output will depend on these only. Now let's just say my next condition is 1, 0, 1, 1. So these output will depend on 1, 0, 1, 1 only. These output will not depend on previous values. So output only depends on the present value of input. So this is known as combinational circuits. Okay, there is no feedback present here. There is no feedback. From output, nothing is going back to input. So output will depend only on the present value of input. So this is known as combinational circuits. Okay, so let's take our first design example. What we need to do here, it is written gray code. Okay, it is written gray code. I hope you will be able to understand. So what you need to do, you need to design a circuit which will detect the decimal number 5 to 10 in a 4-bit gray code. Let's understand what does this want to say. So let's just say you will design this circuit. This circuit I will design. What this circuit will do? This circuit will take 4-bit gray code input. This circuit will take 4-bit gray code input. And detects means it will produce one output. How it will produce one output? So let's just say it is taking this gray code input. Now if the decimal equivalent of this particular gray code, let's just say if decimal equivalent of this particular gray code is 6, then your output will be high. Detecting means output is high. How do you detect? Let's just say at the output I connect a bulb. At the output here I connect a bulb. And if the decimal equivalent of this input is 5, then output will be high. That means the bulb will turn on. So detecting means this, output high or low. If I am saying it is detecting, that means output is high. If I am saying it is not detecting, that means output will be low. And let's just say if I apply an input whose decimal equivalent is 1, I apply a gray code input whose decimal equivalent is 1, then what will be your output? Output will be low. Output will be low. And if you connect a bulb here, so here 0 voltage, here also 0 voltage, so there is no voltage, so current will be 0 ampere and bulb will not glow. So this is what you mean by detecting. So you need to find the equivalent gray code from 5 to 10. For decimal value 5, what will be the gray code? Can you tell that? First you will convert it to binary because directly you cannot write. So first you need to convert it to binary. What that would be? 0, 1, 0, 1. So this is the binary code for 5. What will be its gray code? You are going from binary to gray. You are going from binary to gray. So 0 binary to gray, that means you are busy, that means you will never look down. So 1 XOR 0, 1, 0 XOR 1, 1, 1 XOR 0 XOR 1, 1. So this will be your gray code equivalent. So if your inputs are 0, 1, 1, 1, then this output will be high. This is what this circuit wants to say. Now let's take a random input. Let's take a random input. Let's take a random input as 0, 0, 1, 1. So this is my input 0, 0, 1, 1. Now I am asking you, you have designed this circuit, will this glow or not? Output will be 1 or 0. So tell me, this is the input. This is what? This is a gray code input. Our input is a gray code. So this is a gray code input. What will be its decimal equivalent? We don't know. First we don't know. First we need to convert it to binary. First we need to convert it to binary. If you are GB, if you are ganda bacha, you will always look down. So 0 XOR 0, 0, 0 XOR 1, 1, 1 XOR 1, 0. So this is its binary equivalent. This is the binary equivalent, and what does it represent? Number 2. That means this is actually decimal number 2. So this is actually decimal number 2, and if it is 2, it will not glow, output will be 0. I hope you are getting what we mean here. Now first we will make the truth table, right? And if we know the truth table, we have studied K-maps, we have studied min term, max term. If we have the truth table, then we can write down the output expression. If you remember it, for all, if we see ones, then we will go to SOP. So, and 0 will be our complemented form and 1 will be our normal form, and we will write the expression in SOP if we see only one side the output. If you remember it, say yes or no, you remember it because you have revised it. So let's start. So these all will be my inputs in gray code. This is the equivalent gray code of 0. This is the equivalent gray code of 1. This is the equivalent gray code of 2. This is the equivalent gray code of 5, 6, 7, 8, 9, 10. How I wrote it? 8 times 0, 8 times 1. 4 times 0, 4 times 1, 4 times 1, 4 times 0. This is how we write the gray codes. For initial 16 values, we have written the gray codes when we study about gray codes. What did I tell you? 8 times 0, 8 times 1. 4 times 0, 4 times 1, 4 times 1, 4 times 0. 2 times 0, 2 times 1, 2 times 1, 2 times 0, 2 times 0, 2 times 1, 2 times 1, 2 times 0. 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0. Right? So, for which values it will be high? So, if your decimal equivalent is 5, this will be high. If your decimal equivalent is 6, this will be high. 7 high, 8 high, 9 high, and 10 high. For these values it will be high, for rest of the values it will be low only. For these values it will be low. Although I could have written 0 for everyone only, why I am making this dot dot dot? People will get confused. For all these values it will be low, for these 5 values it will be high. Now you need to write down your output. So you can write down your output in this manner. G3 bar plus G3 bar into G2 into G1 plus 0, sorry, G3 bar into G2 into G1 into G0 plus G3 bar into G2 into G1 bar into G0 plus G3 bar into G2 into G1 bar into G0 bar plus, and in that manner you could have written, right? But this is how we will not do it because it will take a lot of time. What we have K-maps. So we will use K-maps. Let me put the charger. Try making the K-maps on your own and write down the final expression on your own. Then let me put the charger in between. Okay, try doing it on your own. Yeah, so let's start now. So for 0 1 1 0, look, I have written G3 G2 G1 G0. That means this I am assuming as MSB and this I am assuming as LSB, because this is how we usually write it. This is the habit we have. This is our MSB, this is our LSB, ABCD in, if you remember it, right? So G3 0 1 1 1 0 1 1 1, that is 1. So 0 1 1 1, this is 1. Now 0 1 0 1, so 0 1 0 1, this is 1. 0 1 0 0 0 1 0 0, this is 1. 1 1 0 0 1 1 0 0, this is 1. 1 1, sorry, 1 1 0 1 and then 1 1 1 1. So 1 1 0 1 and then 1 1 1 1. So this is what you are getting, right? This is the K-map you are getting. So here I can see a quad and this is also a quad. So 2 quads I can see. And if we check in this one, so how we will write Y? So what do we see here? In the first quad, G2 is the same and here G1 bar is the same. Plus in the second quad, what is same? G0 is same. In the second quad, G0 is same and G2 is same, right? So this is the final our output. So now I can now I can draw my equivalent circuit. How will I draw my equivalent circuit? So what do I need to do? First I will take the G1 bar. First I will take the bar, G1 bar I need to take. Let's forget it. This is this is your G1, so G1 bar I am taking, and then G2, and then multiplication of both of them, G1 bar into G2, G1 bar into G2, and then here there is G naught, G naught into G2, and then there will be addition of both of them. Addition of both of them. Okay, so this input is G1, so here you will get G1 bar. This input is G2, which is same as this input. G2 is same as this input, so you can connect both of them together. So G2 will come here as well, and this input will be G naught. So G naught, here what you will get, G1 bar into G2, and this will be G naught G2, and if you add them up, this will be your output, G1 bar G2 plus G naught G2. Okay, so what you can do, you can go to the user and you can tell him that, sir, this is your IC. If you put G1, G2 and G naught, G1, G2, G naught and G2, if you put these kind of inputs, it will produce the output of, it will produce your high output when the decimal equivalent is 5 to 10. Okay, so this is the IC that you have designed. You can put that in a box and you can tell that, sir, if you put these kind of inputs, it will give you high output for 5 to 10. Let's take another example. You have to design a circuit to detect that decimal number 13579 in a 4-bit 5 to 11 BCD code. So first thing is that we don't know what is 5 to 11 BCD code. So no need to worry, we have studied the BCD code, so we have enough aptitude to understand that. In 8241, what was the meaning of that? That 8421. It is the value of base, right? Place value of 1, place value of 2, place value of 4, place value of 8. So similarly, place value of 1, place value of 1, place value of 2, place value of 5. So it will detect 1357. So this circuit you need to make, and detect means it will give high output or low output. So this is the circuit, I will call it. It is a circuit, and my inputs could be, let's say, what example, A, B, C, D. Okay, so I have taken A, B, C, D as example. So let's just say if my input is 0, 0, 0, 1. So what does this represent? 0, 0, 0, 1, 0, 0, 0, 1. That means this is 1. If this is 1, that means output will be high because it will detect 1. If my input is 0, 0, 1, 1. So what this will represent? 0, 0, 1, 1. What this will represent? 1 plus 1, 2. This will represent 2. So my output will be low. Here output will be high, here output will be low. So in that manner you need to design. So here I am not going to write all the possible inputs. Here I will only write all the inputs which will give me 1. Because I do not need to look at 0. Here I was not looking at 0. I am looking only at 1. So I will write down all the inputs which will give me 1. So which all input will give me 1? Tell me. 5, 2, 1, 1 is there. What we need to detect? 1, 3, 5, 7, 9. So tell me for which inputs we can get 1. 0, 0, 0, 1. Here we will get 1. 0, 0, 1, 0. Here also we will get 1. Now how I can get 3? So 0, 1, 1, 0. 0, 1, 0, 1. This is how I can get 3. What about 5? How I can get 5? 1, 0, 0, 0. This is how I can get 5. How I can get 7? So 1, 1, 0, 0. 5 plus 2, 7. There is another way. 1, 0, 1, 1. How I can get 9? 5 to 7, 8, 9. So 1, 1, 1, 1. So for all these input, your output will be high. And for rest of them, it will be low. You can try on your own. For rest of the inputs, your output will be low. Okay, so for all these inputs, your output will be high. So there are 3, 3, 6, 7, 8 cases. Okay, so let's try making a K-map. So 0, 0, 0, 1. 0, 0, 0, 1. 0, 0, 1, 0. 0 0 1 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1 0 1 0 1 0 1 1 0 0 0 1 0 0 0 1 0 0 0 1 1 0 0 1 1 0 0 1 0 1 1 1 0 1 1 1 1, sorry, this is 1 0 1 1, sorry, and luckily 1 1 1 1 is also there, so 1 1 1 1. So this is the K map we are getting. Very easy K map, no quad is there. We are not able to make any quad here, but the result will be interesting. Okay, so these are very examples. Okay, these are not standard circuit, so you do not need to mug it up that what will be the output of the circuit which will detect 1 3 5 7 9 in a 4-bit 5 to 1 1 BCD code. In the examination you will do it. If this question is coming, you will do it in the examination. You can do this process. You do not need to mug it up the final answer. But in the next lecture onwards, we will study about standard circuit. So there you might need to remember some particular outputs. But that also, there also I will tell you some trick or some way to remember the things. Okay, so no need to worry about that. So here, what will be my y or f? If I am writing f, so what will be my f? So in this one, if I check, so here a bar is not changing and c bar d, plus in this one if I check, c bar d bar is not changing, c bar d bar is not changing, and a is not changing, a c bar d bar, a c bar d bar. In this one if I check, cd is not changing and a is not changing, so a cd, plus if in this one I check, so here a bar is not changing and c d bar is not changing. So this is your final output, right? This is your output. What you can do in this one, you can take a bar common here, a bar common here, so this would be c bar d plus c d bar, and you can take a common here, it would be c bar d bar plus c d, right? I can write this one as a bar c XOR d plus a c XOR d bar. Say yes or no? So what is your f? Now you need to write down it in, you need to write this on your own. What will be your final f? I think you should do all this process on your own, because this is just the previous chapter thing that we are repeating here. So if you write down this expression, you can reduce it more. So what will be the final expression? So final expression of f is a XOR c XOR d. Say yes or no? A XOR c XOR d, because this is x bar y plus x y bar. So a XOR c XOR d, and since these are three inputs, so I can write it in this manner as well, right? So this could be also one of your answer. Now we need to do the circuit implementation. So how we will do it? Very easy. Just 3 input XOR gate is not possible, I told you already. So we need to make two input XOR gate. So this will be the equivalent circuit ACD. So you can tell them that sir, ACD would be there, and it will in 5 to 1 1 code, it will detect the output 1 3 5 7 9. Well and good. So here it is A XOR C, here it is D only. So final output is A XOR C XOR D, which is your output F. Okay, so that's the correct answer. Let's move towards our next design example. So what you need to do, you need to produce 2's complement of a 4-bit binary number, ignore sign bit. Don't do it on your own. Before, like, first you need to see the truth table, then you can do it on your own. So what we are doing, IC is there, we are giving a 4-bit input, 4-bit binary input, and it will produce the 2's complement. 2's complement means there will be 4 outputs only. Say yes or no? If I am giving 4-bit input, what is the 2's complement of 0 0 1 0? It will be some 4-bit only, no? It will be some 4-bit only. So output will also be in 4-bit. So 4-bit input, 4-bit output. How I am denoting the bits? A B C D only. So A B C D. This is our circuit, which will give output as y3, y2, y1 and y0. Okay, but there is very like interesting thing. If my input is 0 0 1 0, so what do you expect the 2's complement of that? What is the input? 4-bit binary input. Okay, input is 4-bit binary input. So generally if they are saying that take 2's complement of a binary input, that means what you will say that, sir, for 2's complement first we need to convert it to sign magnitude form. So I will consider this is 1 and then I will convert it to sign magnitude form, which will be plus 1. So it will be 0 0 1 0. Okay, now it is plus 1. Now I can take 2's complement of that, which will be equal to this only. So you will say that, sir, 2's complement of this number is this number. But generally I will tell you one thing, if they are talking about 2's complement, that means they are talking about negative numbers only. Okay, if they are saying that take 2's complement of a binary number which is this, that means they are expecting that you will take the 2's complement of this, considering here there is bit 1 already. So they are expecting that you will take 2's complement of -2. This is 2 only, no? So if they are saying that take 2's complement of binary number, if they are saying sign magnitude form, then it is different. If they are saying that take 2's complement of binary number this, that means how you will take the 2's complement? 1 as it is and 0 1 1 0, sorry, 0 1 and 1 1. So this is the 2's complement. So this is the 2's complement of 0 0 1 0. I am telling you the actual scenario, like how in digital circuit or how digital designers talk. So if they are talking about 2's complement, that means they are already talking about negative number. So 2's complement of a binary number, if they are asking, that means they are considering this number is already negative, this 1 bit is already there. You need to take 2's complement of this. So how will you take 2's complement of this? 0 1, and since you got 1, you take complement of these two. Okay, so how will I make the truth table? So I am considering this is -0, already 1 is there, already 1 is there. So I will start from the back 0 0 until I get 0, until I get 1 I will not change anything. So for 0 0 0 it will be 0 only. Here I will start from here until I get 1, until I get 1 I will not complement, after that I will complement. So all these bits will be complemented. I will start from here until I get 1, I got 1, these bits will be complemented. I will start from here, I got 1, so these bits will be complemented. Starting from here 0 0 1, this will be 1. Starting from here all these are complemented. Starting from here these are complemented. So you can see 1 0 0 1, 0 0 0 1, 1 1 1 0, 0 1 1 0, 1 0 1 0, 0 0 1 0, 1 1 0 0, 0 1 0 0 and 1 0 0 0. This is the truth. Yeah, so one error I did in the truth table, which is this. So here it should be 1 only, no? So this is one error, 1 0 1 1. So if you do these kind of error, it would be very tough because the whole solution will go wrong. Okay, so what is your y3 in my min terms? If you write it in min terms, that is 1 2 3 4 5 6 7 8, 5 6 7 8. So if I represent y3, so what it would be? 1 to 8, no? So 0 1 2 3 4 5 6 7 and 8, right? Min terms. So I can see a quad here. Let's say move it off. It was 1 1 1 1. So I see a quad. I see a quad here. I see a quad here. I see a quad here as well. And this guy will go alone. So for this guy, the expression is A, B bar, C bar, D plus A bar, B plus A bar. Here what is changing? Here A bar is same and what is same? And D is same. Plus in this one A bar is same and C is same. So if you go in a good interview, these kind of questions will be asked there. The design a circuit, they will not ask the standard circuit, half adder, full adder, because everyone knows it. But here you need to use your own brain. So this is how you will design in front of them, and you will tell that, sir, this will be my output. Now I can design it. Now you can design it very easily, right? A will be there, V bar will be there, you can design it. We will see the design, but since I have the expression, I just need to use the logic gates now. Now what about Y2? What about Y2? So Y2. So 1, 2, 3, 4. At least till 4 it is there. 1, 2, 3, 4. 9, 10, 11, 12. 9, 10, 11, 12. So 1, okay, starting from 1, 2, 3, 4, not from 0. So 1, 2, 3, 4, 5, 6, 7, 8, 8, 9, 8, 9, 10, 11 and 12, right? So this is 1, and then I can see quad here. 2 quads I can see directly. One quad is this, and another quad is this. Okay, so what will be your Y2? So Y2 is B C bar D bar plus B bar plus B bar, and here what is same? B bar D plus here what is same? Again B bar is same, and here in this one C is same. So B C bar D bar B bar D. What about Y1? So 0 1. So Y1 is 1 2 3 4 5 6 7 8 9 10 11 12 13 14. Does something click to you? 0 1 2 3. Next is 2 3. Next is 4 5 6 6. Next is, this is 7. This would be 8. This would be 9. Wait a second. 0 1 0 1 2 3 4 4 5. This is 6 7. There is something wrong. Let me check. 0 1 2 5 6 7 8 9 10. Let me check it. Yeah, so nothing is going wrong, everything is going fine only. So we have 0 1 2 3 4 5 6 7 8 9 8 9 10 11 12 13 14 15. So these are the numbers, no? 13 14. So yeah, these are the numbers. So here you can directly see this and this. So what is your Y1? Y1 seems to be C bar D plus C D bar, which will be C XOR D. Okay. What about Y0? What is your Y0? Y0 is simply equals to D. Y0 is D only. Say yes or no? If you check, Y0 and D both are same, because first will be, at least this bit will be copied as it is, no? So Y0 is equals to D. So Y0 is equals to D only. I will not have to make the KMap. So these are the expression I have got. F3, here I have written F3, but it would be Y3, Y2, Y1, Y0. Y3, Y2, Y1 and Y0. Okay, so these are the expression I have got. So how will I implement it? Now this circuit will look very complex. So better to represent in this manner. So you have A, this will be A bar, this will be A bar, this will be B bar, this will be C bar, and this will be D bar. Now what you need? A into B bar into C bar into D bar. So A is coming, B bar is coming, C bar is coming, D bar is coming. So this will be A into B bar, C bar, D bar. What else you need? A bar B. So A bar is coming into B is coming. So this is A bar B. Here A bar C, and here it would be A bar D. All will be added and you will get here what was that? F3, Y3. So you will get Y3. Similarly, you can do it for Y2. Similarly, you can do it for Y1. Similarly, you can do it for Y0 as well. This will be your Y0. This will be your Y0. This, sorry, D bar, not D bar. Y0 will be this. This will be your Y0. So you can do the same for Y1 and Y2. Okay, just just the feel of the question I wanted to give you. Okay, just the feeling I wanted to give, that how to solve these kind of problems. So you must have got the feel now, right? Let's move towards our next circuit. So design a combinational circuit which will produce ones complement of 4-bit number. Ignore the sign bit. So ignore the sign bit. You need to represent a ones complement. So ignoring the sign bit, what will be the ones complement of this? All bits will be complemented, no? So these are just a complement. So this will be, all bits will be complemented. All bits will be complemented. 1 0. It would be 1 1 0 1. Simply all the bits will be complemented. So this will be 1 1 1 1 1 0 0 0 0 0 0 0 0 1. All 1 will convert it to 0. All 0 will convert it to 1. 0 0 0 0 1 1 1 1 0 0 0 0 0 1 1 0 0 1 1 0 0 1 1 0 0. This would be 0 1 0 1 0 1 0 1 0 1 0 1 and 0. If you see 0 1 1 0, what will be the two ones complement? 1 0 0 1. That's it. So I am writing ones complement here only. So what did you understand? Y3 is equals to A bar, Y2 is equals to B bar, Y1 is equals to A bar, and Y0 is equals to D bar. So if I am having A, B, C, D as input, so these will be our Y3, Y2, Y1 and Y0. Say yes or no? A, B bar, directly this is the output. This is our ones complementer circuit. Ones complement circuit. Say yes or no? Right? Let's move our next question. Design a combination circuit which will take 3-bit binary input and produces an output equals to the square of input in binary form. So what we are doing here? 3-bit binary input we will take, and you will produce some output. So in output, how many bits will be there? Give me the answer. In output, how many bits will be there? Let's check it. So let's just say if this is my input, what this circuit is doing, which will take 3-bit binary input and produces an output equal to the square of the input, equal to the square of the input. So this is, what is this? This is 1. In decimal, this is 1, right? What is the square of 1? 1 only. So your output will be 0 1 1. If your input is 0 1 1, so what is this number? This number is 3. What is the square of 3? That is 9. So what will be your output? Output will be 9. How can you represent 9? 0 1 0 0 1. So for that you require 4 bits, right? If my input is 1 1 1, what is this number? This number is 7. What is the square of 7? That is 49. To represent 49, how many bits you require? Think and tell me about it. 6, right? Because with 6 digits, what is the maximum? With 4 digit, what is the maximum number you can get? 15. That is 2 to the power 1 minus 4. With 5 digits, you will get 2 to the power 5 minus 1. That is 31. Here you will get 15. With 6 digits, you can get 2 to the power 6 is 63. 63 minus 2 to the power 6 is 64. So 64 minus 1, which is 63. So 49 cannot be covered in 5 bits. You need 6 bits. So output will be of 6 bits. Output will be of what? It will be of 6 bits. So output will be of 6 bits. 1, 2, 3, 4, 5 and 6. So output will be of 6 bit. Y5, Y4, Y3, y2, y1 and y0. Okay, and this is your input which I must have written in ABC. So let's check it out. So this is decimal equivalent 1, 0, 1, 2, 3, 4, 5, 6 and 7. Square of 0 is 0 only. Square of 1 is 1 only. Square of 2 is 4. So this is 1, 2, 4, 8, 16, 32. Square of 3 is 9. 9. Square of 4 is 16. Square of 5 is 25. 0, 25. So 1, 1, 0, 0, 1. So 16 plus 8 is 24. 24 plus 1 is 25. 36. So 32 plus 4. And 49. 49. So 32 plus 16 is what? 48, right? So 1, 1, 0, 0, 0, 1. Okay. Well and good. No issue. Now tell me one thing. Will I make the K-map here? No, for y5, if I need to write down y5, what that y5 would be? Y5 would be a into b into c bar plus a into b into c, right? y5, it is 1 here only. So a into b into c bar plus a into b into c, which can be reduced to ab. This is your y5. Well and good. Okay, next I have only example only. So this is your y5. What about y4? So for y4, you can see a into b bar into c bar plus a into b bar into c. B bar into c. So you can take ab bar. So c plus c bar is 1. C plus c bar is 1. This is your y4. What about y5? What about, no, sorry. What about y3? What about y3? What about y3? So a bar into bc plus y5, a bar into bc plus a into b bar into c. B bar into c. A bar into bc plus a into b bar into c. A into b bar into c. Okay. So a XOR b into c. A XOR b into c. What about y2? Y2. So this is your a bar b c bar. A bar b c bar plus a b c bar. A b c bar. So bc bar. A plus a bar is 1. What about y1? Y1 is always 0. And what about y0? Y0 is equals to c. 0 1 0 1 0 1 0 1. Y0 is equals to c. That's it. So these all are the expressions. This is the expression. This is the expression of y2, y1, y0. So you can implement that. I am not implementing. How will you implement y1? Simply you will ground it. This is your y1. Y1 is 0. So you will simply ground it. Okay. Y0 is c. Y4 is a b bar. Y3 is a XOR b into c. And y5 is ab. Okay, that's it. Okay, this is the answer. Let's see the next question. Design a combinational circuit which takes two 2-bit binary input. Two 2-bit binary input. That means it will take two inputs. It will take two inputs, but every input will have 2 bits. That means it will take the input A and B. Let's just say it will take the input A and B. So this input A and B, these inputs will be of 2 bits. These inputs will also be of 2 bits. So these inputs will be A1, A0. Same goes for this B. These inputs will be B1, B0. So better we should represent it like this. So A have 0 to 1, B have 0 to 1, B0, B1. So two inputs are there and it will produce a single output. It will produce a single output. The output will be high. the output will be high when the decimal equivalent of the input is, when the decimal equivalent of the input is circuit A even odd number and circuit B A is for odd number. Two questions are there. First one is for odd number and second one is for even number. What they are saying, two bits produce a single output, the output will be high if the decimal equivalent of the input is of the sum of the input is, okay, really sorry for all these blunders, of the sum of the input is, of the sum of the input is, of the binary sum of the input is. So let's just say this is my input 0 1 1 0. I am saying A1 is my MSB and A0 is my LSB. So what does this represent? 1. And what does this represent? 2. 1 plus 2 is 3. So what it is? 3. So if it is an odd number, it will be high. This is what our first question is saying. Our second question is saying, let's just say if this was my 1 0, 1 0. So this is my MSB. So this is 2. This is also 2. 2 plus 2 is 4. So in the second question, this one will be lit. Okay, if this is the input, in the second question it will be lit, and if this is the input, in the first question it will be lit. I hope you must have understood the problem. So let's write down all the possible combination. So what all can happen? That 0 0 is 0 0 is added with 0 0, 0 1 is added with 0 0, 1 0 is added with 0 0, and 1 1 is added with 0 0. So all the possible combination of 4 bits we have written. That 0 0 is added with 0 0, 0 is added with 0 1, 0 0 is added with 1 0, 0 0 is added with 1 1, 0 1 is added with 0 0, 0 1 is added with 0 1. So basically all the 16 possible combination I have written, 8 times 0, 8 times 1, 4 times 0, 4 times 1, 4 times 0, 4 times 1, because anything can be coming into the input side. 2 times 0, 2 times 1. So 0 0 is added with 0 0. What will be the sum? 0. 0 0 is added with 0 1. What will be the sum? 1. 0 0 is added with 1 0. So this has the place value of 1, this has the place value of 1. Sorry, 2. This has the place value of 1, this has the place value of 2. So 0 plus 2, 2. 0 plus 3, 3. 1 plus 0, 1. 1 plus 1, 2. 1 plus 2, 3. 1 plus 3, 4. 1 plus 3, 4. 2 plus 0, 2. 2 plus 1, 3. 2 plus 2, 4. 2 plus 3, 5. 3 plus 0, 3. 3 plus 1, 4. 3 plus 2, sorry, yeah, 3 plus 2, 5. 3 plus 3, 6. I hope the addition is fine. 1 2 3, 1 2 3 4, 2 3 4, 5, 3 4 5 6. Okay. So what is about YA? YA will lit for odd number. This is for odd, and YB for even. Let's check the odd number. 0 is not a odd number, so this will be 0. This will be 1. This will be 0. This will be 1. This will be 1. This will be 0. This will be 1. This will be 0. This will be 0. This will be 1. This will be 0. This will be 1. This will be 1. This will be 0. This will be 1 and this will be 0. Let's check back again. 0. Let's solve this one. Even 0 1 1 0 0 1 0 1 1 0 1 0 0 1 0 and 1. So these will be just the complement of each other, no? This will be just the complement. YA would be complement of YB, right? Because this will lit for odd, this will lit for even, so both are complemented only. Very easy thing. So all these are correct only, right? If these are coming complement only, so I hope I have written it correctly. Okay. So we can either find it for YA or we can find it for YB. Let's try for YA. So what is your YA in terms of min terms? So that is 1 3 4 1 3 4 6 1 3 4 6 9 11 12 14 9 11 12 14. So 1, 3, 4, 6, 9. So this K-map I will not draw. Start from 1, 1, 3, 4, 6, 7, 9, 10, 11, 12, 13, 14. So what about this? So this is a chord I can make. And this is the chord I can make. So I can make 2 chords. Okay. So what will be your, this is for YA. So what will be your YA? What do you think? So here in this chord, which one is constant? Y0 is constant and Y0 is constant and Y2 bar is constant. Plus in this chord, Y0 bar is constant and Y2 is constant. So what you are getting? Y0 XOR Y2. So this is your YA. YA is Y0 XOR Y2. So what will be your YB? YB will simply be Y0 XNOR Y2. So we did all this calculation, then we got to know that our answer is very straightforward. So what will be the design? So these kind of questions can come in your examination. They can simply ask you the output. So there you will have to do all these calculations, the 0 0 0 0 1 1. So for which one it will be even or odd. So in that manner you need to do the calculation. So and then simply an inverter after that, and this is your Y0, this is your Y2. So this will be your YA and this will be your YB. Well and good. Are you getting this point? Or how I could have designed it? What I could have done is that 3-bit input is not possible actually. So what I could have done is that this, no sorry, here I will get Y0 XOR Y2, right? And then another, if I am having another XOR gate, this I could have done. Here I will put Y0, here I will put Y2, and here I will put control, and this is my final output, final output, which I am denoting as Y. So if C is 0, then my Y would be Y0 XOR Y2, and if C is 1, what will happen? Here you are getting Y0 XOR Y2, right? XOR with 0 will be this. XOR with 1, what that would be? Y0 XOR Y2 XOR with 1 will be the bar of that. And what will be the bar of that? It would be this. So this is known as control unit. So which you can put at input. Okay. So you will put that in a box and you will keep this bit outside. Keep this bit outside. This bit is C. This bit is C. So you will keep this bit outside C and you will tell to the user that, sir, if you put C equals to 0, no, then your output will show that your sum is odd, right? Sir, if you put C equals to 0, your output will show that the sum is odd, and if you put C equals to 1, then your output will show that the sum is even. This is what you can tell to your user. That, sir, there are 3 inputs, Y0, Y2, and C is the control bit. If you put C equals to 0, then this should be the output. If you put C equals to 1, then this should be the output. So this is how also you can design the circuit. Okay, just a way I am telling. So in that manner you can design it. And in the examination these kind of questions can come. Okay, so you should be aware of that. For YB we are not doing, we are only doing for YA, because we know YA this will simply be complemented. So let's solve this question. You need to design a 3-bit, for a 3-bit input, design a combinational circuit which detects majority number of 1 or minority number of 0. Both are same thing, no? If 1 is in majority, that means 0 will be in minority. So for a 3-bit input, you need to design a combination circuit which will detect majority number of 1s or minority number of 0. That means if my input is 0, 0, 1, 1 here, I am designing majority number of 1. So here 1 bit is coming one time only and 0 bit is coming 2 times. That means it will be low. If my input is 0, 1, 1, then 1 bit is coming 2 times and 0 bit is coming 1 time. That means my output will be 1. So this is the meaning of question A. Question B is just opposite of that, right? Majority number of zeros, that means minority number of 1. Are you getting this point? So let's write down all the possible condition. This could be the possible condition. So if here, what is the majority? Majority is 0 only. What is this? This is majority number of 1s. Majority number of 1s. And this is majority number of zeros. Number of zeros. So here 0 is in majority, 1 is not even there. So this is 0. Here 0 is in majority. So again this will not be high. Here also 0 is in majority, this will also not be high. Here 1 is in majority, high. Here again 0 is in majority, not high. Here 1 is in majority. Here also 1 is in majority. Here also 1 is in majority. And for this, here zeros are in majority, zeros are in majority, zeros are in majority. Here 1 is in the majority, zeros are in majority, and rest all will be 0. So if you can solve it with SOP as well, you can solve it with POS as well. But you will get a very interesting result here. YA is M3, 5, 6, 7. And let's try solving YA. You will get a very interesting result which you will remember as well. Okay. So A, B, C. So 0, 1, 2, 3, 4, 5, 6, 7. Okay. 1, 2 and 3. This is your A bar A. This is your B bar C bar, B bar C, BC, BC bar. So what is your Y? Y is BC plus, here A is constant and C is constant, plus AC. Here A is constant and B is constant. So AB. So Y is AB plus BC plus CA. Do you remember anything about this expression? Do you remember anything about this expression? This is a self dual function, right? Self dual function. If I have written YA in this manner, okay, let's not do it. We will again make the K-map. So this is one of the expression. Let's make the K-map again. Now I am doing it with the SOP. No, I have already done it with SOP. Now I will do it with POS. So this is A plus B plus C. So this will be A, this will be A bar. This will be 0, 0, sorry. B plus C, B plus C bar, B bar plus C bar, B bar plus C. So where 0 will come? 0, 0, 0 and 0, right? One, 2 and then 3. So Y is equals to A plus B. I am writing for this one, A plus B into B plus C, and let's write for this one. Here C is constant and A is constant, so C plus A. So A plus B into B plus C into C plus A. So y, which we got, AB plus BC plus CA, all are equivalent only. I am again making it for YA only. This was for YA. This is also for YA only. So this is your YA. Again, this is your YA only. So YA has got two expression till now. This one and this one. So will you be able to remember it? AB plus BC plus CA is equivalent to A plus B into B plus C into C plus A. Right? Okay. Now one more expressions we can get. How we can get more expressions? So again, let's write down this thing. So A bar A, B bar C bar, B bar C, B C, B C bar. 1, 1, 1, 1. I will do very interesting thing. What I will do? I will just make this, okay, and I will keep them alone. Let's see what we get. This is not the minimized term. That's for sure. This is not the minimized term. But let's see, we will get something interesting here. What is that? Y is equals to BC plus, what about this? It would be A B bar C. What about this? This would be A B C bar. So what I am getting? BC plus A as common. This would be B bar C plus BC bar. So it would be equals to BC plus A into B XOR C. So one more Y expression you got, that is BC plus A into B XOR C. You can do the same thing for AB. What you can do? One more thing I will show you. So let's remove it off because you already know this is already written here. Okay. So what you can do is that same example is there, 1, 1, 1, 1. This is A bar, this is A. So what I will do is that now I will keep A and another number, that is C. Let's keep A and B as constant. Okay, let's keep B, A and B as constant. So we are keeping these two constant, this and then this. If you remember, we solved an example like this as well in assignment problem. So there I told you that later on I will tell you why they are equivalent. So now I am telling you why they are equivalent. So if I am doing this example, so here for this pair A and B are constant. For this pair A B bar C, and for this pair A bar B C. So A B C can come common, A B bar plus A bar B. So what is the answer you are getting? A B plus C A XOR B. Right? So this is your Y. Similarly, Y could be, for BC we have done, so AC plus B A XOR C, and Y is BC plus A B XOR C. Also your Y is AB plus BC plus CA. Also your Y is A plus B into B plus C into C plus A. And also your Y is summation M 3, 5, 6, 7. And all these are same only. And if you remember in self dual, I told you this is a self dual function, because if this is the dual of it, no, dual hai, this is the dual, right? This is dual, this is the dual of it, and this is same. So this is a self dual function as well. Self dual function. Okay. Now let's talk about YB. If I talk about YB, so YB is equals to YA bar. And what is YA? YA is AB plus BC plus CA, AB plus BC plus CA, and it is self dual function. If it is self dual function, then do you remember, if it is self dual, then what will be its bar? So first we take the dual and then we take individual component. First we take dual and then we take individual component. If you need to go from here to here, what you will do? First you take the dual and then you take individual complement. If you remember it, right? First you take dual and then you take individual component. So dual of this will be this number only. Now I need to take complement of that. So what I will do? Individual complement. So this I have already taught in that chapter where we studied about duals. So this could be one of the expression, or what could be the other expression? This same expression is there, no? A plus B plus B plus C plus A. Dual of this will be the same value. Dual of this will be the same value. Then I can take individual component. Tell me one thing, that this is also YB. The other expression of YA is this. AB plus C A XOR B. Now if I am saying that take the complement, so what I am doing, since I know this is self dual function, so I can take individual complement now. Is that correct? Is that correct? That I take this complement? No, you need to take individual complement. So this complement you will take. And if there are two complements, that means both complements will get cancelled. So basically complement to complement, this will get cancelled, no? A, this how you can write? A XOR B bar. Then another bar is there, so another bar. This will get cancelled. So A XOR B you will get. So this will be A XOR B only. So individual you component you need to take. I have seen like people generally will take this is the complement, individual complement. So this will again be A XOR B only. So what could be the other expression of YB? That would be A bar B bar plus C bar A XOR B. It could be A bar C bar plus B bar A XOR C. It could be B bar plus C bar A bar B XOR C. So YB and YB. What else YB is? Summation M. This you might not be able to remember, so no worry, even I don't remember this. But I remember this one, 3, 5, 6, 7, so which is 0, 1, 2, 4. 0, 1, 2, 4. So this is your YB. Are you getting this point? So these many expressions we can write. Right? So what is the conclusion? Majority number of ones detector, that is 3, 5, 6, 7, and majority number of zeros detector is 0, 1, 2, 4. These are the expression, these are the output expression. AB plus BC plus CA, A plus B into B plus C into C plus A, AB plus C A XOR B. Which of them are the most important ones? This is the most important one, okay, and AB, this one is most important. So I hope from now onwards you will remember this. So all these expressions can be written in these manners, because in MSQ these kind of questions will be coming. In MSQ they can frame a lot of problems and a lot of options, then they can say which of them are equivalent. So that's the thing, okay. So I hope this lecture is clear and you are building the basics of our combination circuit. So you have built the basic that what we are going to do in the combination circuit. None of them was a standard circuit, and no one will actually teach you all these kind of circuits. They do not really teach these kind of circuits because they think that this is not standard. But we also need to deal non-standard circuit as well, because they can come in your examination. Standards will come, but non-standard we have to deal. So we have dealt it in very first lecture only, so that your concept building up is good. Okay, then no answer you need to mug up. Okay, you do not need to mug up these values, you do not need to mug up these values here. You also do not need to mug up these answers. Okay, you don't need to mug it up. Even I don't remember the final output, but in the last one when I told you majority number of ones detector or majority number of zeros detector, then you can keep it in mind. If you forget it as well, then you can quickly derive it as well in the examination. You will see 3, 5, 6, 7. Okay, that's it. This is AB plus BC plus CA, and there are more expression that I know. A plus B into B plus C into C plus A, or AB plus C A XOR B, AC plus B A XOR C, BC plus A XOR B XOR C. Okay, and same for the dual. It is a self dual function, so this thing happens. So this is a very important function. That's why we are dealing it here. Okay, then. So yeah, that's it from my side. Let's meet you in the next lecture where we will study about the standard circuits. Okay, then. Yeah, thank you very much.